Welcome to the AP Physics video lecture. This is on torque and rotational motion. This section is on rotational kinetic energy. We'll start off by looking at the energy both in the line world and the circular world. The gravitational potential energy is the same in both, which is defined by mgh. The gravitational potential energy is the same in both the line and circle world, does not change. On the left-hand side, you see a block sliding down, and you can see that the gravitational potential energy is converted into linear kinetic energy, sometimes referred to as translational energy. The kinetic energy that it has at the bottom is defined by 1/2 mv squared, and the unit is referred to be joules. So the question is, describe what the gravitational potential energy is converted to when the block slides down the ramp. Assuming the system is closed, we can use conservation of energy. All of the gravitational potential energy is converted to the linear kinetic energy. mgh is equal to 1/2 mv squared. On the right hand side, it's now a sphere that rotates down a ramp. The ramp has the same height as before. The theta is the same. The difference, though, is that this is a sphere, not a block. Here, though, it's actually going to go down with something called rotational kinetic energy. The rotational kinetic energy is defined by 1/2 I, which is rotational inertia, omega, which is angular velocity, squared. The unit is the same, which is joules. So the question here is, describe what the gravitational potential energy is converted to when a ball rolls down a ramp. So the answer is, it is converted into linear kinetic energy and rotational kinetic energy. So that mgh is equal to 1/2 mv squared, which is the linear kinetic energy, plus 1/2 I omega squared, which is the rotational kinetic energy. So it has both rotational kinetic and linear kinetic energy. Let's look at the cause of the rotational kinetic energy. We saw the equation was K is equal to 1/2 rotational inertia omega squared. Let's take a look at these two examples. When the ball goes down a ramp, two things can happen. It can either slide, which is on the left-hand side, or roll, which is on the right-hand side. You can denote by looking at the arrows. On the left-hand side, the object will slide down if there is no friction. On the right-hand side, the objects will rotate or roll when there is a friction force. You're asking why. Let's take a look at the free body diagram for a rolling ball. Here are all the different forces. The forces that is going to the right is the force applied. What is going down is the force of gravity. What is going up is the force normal. And what is going left is the force friction. But notice the force friction here is at the circumference of that ball. So here, first of all, please notice that the force of gravity and the normal force cancels because it's not going up or down. So the vertical parts cancel. The F is the force that causes the object to move to the right. Please note that the friction force here is on the surface and it is applied away from the center of mass. Here is the center of mass. And notice that the force is applied a distance r away. The fact that the friction force is applied at a distance away from the center, there is a torque that introduces the rotation to occur. This should explain to why the object rotates. It is because the friction force is applied away from the center of mass, causing the circular object to rotate. Understand that the friction force actually does zero work here. The reason why is because static friction does not do work because the points of contact of a sphere at each instantaneous does not slide but moves perpendicular to the plane. Take a look there. This should explain that the friction force does zero work. Let's look at the total mechanical energy of a system. Here's the scenario. A ball, which is a thin spherical shell, Rotational inertia equals to 2/3 mr squared. Please understand you do not have to memorize the equation for the exam. The rotational inertia will always be given to you with a radius of 0.25 meters. It starts on top of a 2-meter high ramp at rest. The ball rolls down the rough surface ramp. Graph the total energy at every given step in the scenario. So we are going to look at the conservation of energy equation to do this. At the start, at the ball on top of the ramp at rest, here it is all gravitational potential energy, which is at the start because it is just mgh. And then when the ball is near the top of the ramp, it went down a little bit, but so the gravitational potential energy is less, but what is gained is the kT, which is the I think that's the linear one, so that's the translational kinetic energy, and a little bit of the rotational kinetic energy. So here the gravitational potential energy is converted into both the translational kinetic energy and the rotational kinetic energy. The Kr, which is kinetic rotation, is less due to it having a higher rotational inertia. You don't have to believe me here. I'm going to show you the math to prove it in a bit. Next, at the end, when the ball is at the bottom of the ramp, there is no potential energy, and it's all kinetic translational and kinetic rotation. Notice kinetic translational is still bigger. Okay, so at the bottom of the ramp, zero gravitational potential energy is left because all of it has been converted into the translational kinetic energy and rotational kinetic energy. Notice that the kinetic rotation is still less due to it having a higher rotational inertia. Let's take a look at the equation for it to make sense. So the energy initial is equal to the energy final. The potential energy was the gravitational, so it's UGO. And the energy final is made up of two kinetic energies, KT, which is the translational kinetic energy, and KR, which is the rotational kinetic energy. Make the substitution in. mgh goes in for the gravitational potential. 1/2 mv squared goes in for kinetic translational. And Kr, which is rotational kinetic, is 1/2 I omega squared. Notice I color coded so you see the substitution. So everything's the same here. I just substituted the I, which is the rotational inertia, for what was given. It's in red. 2/3 mr squared. The omega can be substituted as v over r. Okay? Because velocity is equal to r times omega. That's how I'm getting it. Alright? Notice there are some cancellations that does occur. Alright? So do you see the 2/3 here? Cancels out. The 2 and the 2 here cancels out. The let's see here. The r, so the r square on the bottom cancels out. So you're left with an mv squared. That's what you should have. So the right hand side, the new rotational kinetic energy is 1/3 mv squared. That's after I substitute in all the values. Okay? 1/2 and 1/3 looks weird. So what I did is I just found its common denominator, which is 6. So what I did here is I looked at it. So 1/2 and 1/3, the common denominator is 6. So I converted it into its common denominator. All right. So you should look at the numbers in front. Now, take a look at the amount of energy on the left-hand side. So whatever gravitational potential it is, it's going to be equal to 3/6 mv squared plus 2/6 mv squared. If you look at 3/6, which is really 0.5, that is the constant in front. 2/6 is roughly 33%. Okay, so you can think about this as 50% of the energy is kinetic and the 33% of it is rotational. That's like the ratio that they're looking at. Okay? On the exam, they will never ask you to like calculate it, but this is I show you this math to explain to you why kinetic energy is more, because again, this is the 3 over 6 mv squared, and the yellow, which is rotation, is 26 mv squared, which is less. Okay, that should explain why the rotation is a little bit less than the kinetic. All right, that's the math to explain that part. Let's look at this problem. This is the same thing, but the scenario is now it's a solid sphere. The rotational inertia is 2/5 mr squared. Okay, the scenario is the same besides the object. The gravitational potential is everything at the start. Now, this time we're going to start with the math. Okay, same thing here. Gravitational energy is equal to the rotational kinetic and the linear kinetic. We plug in the values. This time the rotational inertia is 2/5 mr squared, and the omega is the same as v over r. Notice the 2's here on top and the bottom cancels. The r squares here will cancel, leaving you this time with a 1/2 mv squared for the linear kinetic energy, 1/5 mv squared for the rotational kinetic. Finding the like terms, which was 10, so I multiplied the 1/2 mv squared by 5, giving me 5 over 10, and I multiplied 1/5 mv squared by 2 to get 2 over 10. Notice at this ratio now. So notice near the top, it has more kinetic energy and it has super less rotation at the because the gravitational potential is converted into both the translational kinetic energy and the rotational kinetic energy. The rotational kinetic energy is less, it due to having high rotational inertia. Here's U at the bottom, which is nothing. It's all kinetic and a little bit more rotational kinetic energy, right? If you look at the math, this is the 1/5 part, the 5/10 mv squared part, right? And this is the 2/10 mv squared part. Again, this can be broken down to like 1/2. So, sorry, it's already a fraction. It could be like 0.5 mv squared. This is 2/10, which is what? Let's see. Yeah, 0.2. Okay, this is 0.2 mv squared. Okay, this is 0.2. This is 0.5. Do you see that ratio? This is why kinetic energy is more for this object and less for rotational kinetic. This is important because when we looked at this example and when we did this, there's an explanation to why the red one goes down first. Okay, so again, we looked at the conservation of energy. E initial is equal to the E final. We made those substitutions. We saw that when a circular object goes down a ramp, there is both the linear or translational kinetic energy, which is defined by 1/2 mv squared, plus the rotational kinetic energy, which is 1/2 I, which is rotational inertia, omega squared. For the first one, it was 3/6 mv squared plus 2/6 mv squared. Then for the spherical shell, which was green, the last one that we did was the solid sphere. It is 5/10 mv squared plus 2/10 mv squared. Notice the ratios are way different here. There are three things that you need to note. One, you should now understand why the red or the solid sphere reaches first and why the green sphere is second to last. The red solid sphere, due to its rotational inertia, had more of its gravitational potential translated into translational kinetic energy, which is 5/10, than rotation, which is 2/10. This means it spends more time moving down that ramp. So that red color is the more time it's basically it explains why it spends more time moving down the ramp. And the blue part is the rotational inertia, the rotational kinetic energy, which explains why it spins in a circle. So the red sphere spends more time moving down the ramp than spinning in the circle. That's what its equation should explain. The green sphere has more energy translated into rotational kinetic energy. That means it spends more time turning in a circle than moving down that ramp because now it's 2-6 rotation and the kinetic was 3-6. Okay? That's it. Make sure that you can understand why certain things reach down the ramp further based on its rotational inertia. Last thing is the angular momentum and rotational kinetic energy question that could appear on the multiple choice of the AP Physics 1 exam. Here's the scenario. A ball of mass m collides with a smooth hanging rod of mass big M and a length L such that one end of the rod is connected to a pivot point that the rod would rotate around if acted upon by a net torque. After the sphere collides with the rod, the sphere sticks to the rod and both objects rotate to surround the pivot point with a common angular velocity. Question 1. Kimberly argues the rod experienced a torque caused by the force of the ball hitting it. Therefore, the angular momentum is not conserved and there is an angular impulse. Please correct the statement. So the answer, Kimberly is wrong when she said that because the rotational collision under consideration here is an elastic collision. The reason why is because it says it right there, which is bolted. The sphere sticks to the rod. That's why it's an inelastic collision, in which means there are no net torque exerted on the system. We know that in inelastic collision, the angular momentum is the same immediately before the collision and immediately after the collision. That means P initial is equal to P final, conservation of momentum. P final minus P initial is always equal to 0. This means it's constant. That is the definition of conservation of angular momentum, or momentum here. Question 2. Anna now argues since the rod is smooth, the energy system is conserved. All the linear kinetic energy from the ball is transferred into the rotational kinetic energy for the rod. Please correct that statement. Well, in an inelastic collision, it sticks together. Energy is converted into non-mechanical energy during the collision. The non-mechanical energy that they're referring to sometimes is the thermal and the energy required to stick the object together. Okay? Therefore, the rotational kinetic energy of the system immediately before the collision is actually greater than the rotational kinetic energy of the system after. All right? So if we take a look at the initial, so the kinetic energy, yes. So kinetic energy for rotation initial is equal to kinetic rotation final. That is wrong. Okay? It is wrong. It is not equal to. It is greater than. Why? Why is it greater than? Is because there is some loss to thermal here. Okay? It's lost to thermal. That is why kinetic energy rotation initial is greater than the final kinetic rotation. All right, so there you go. Hopefully that should help you when it comes to seeing rotational kinetic energy.